Welcome back once again. Let's finish talking about entropy. So, I don't know if you looked at the notes that I posted, the PowerPoint slides that I posted. I've got lecture 20 and 21 in there. I knew we wouldn't get through all of them, so I just went ahead and put enough for both lectures in there. So let's finish up. So we finished up last time talking about so we talked about both constant and variable specific heat using Gibbs Equation for an ideal gas. We looked at that, the nozzle problem. We looked at doing that two different ways. And I said at the very end, I said there is actually a third way, a very common way to do this is what we call the K ratios. Now this is if and only if, double I double F, if and only if we need two things. One, we have an ideal gas. You have to have an ideal gas. Two, if it's isentropic or isentropic. Right? So if something is isentropic, what does that mean? If you don't know what that means, you really should. I'm going to rewrite this, not in cursive. If you don't know what isentropic means, you really should pause at this point and go back and pull your notes. That's important, really important at this point that you do not know what isentropic means. Go look that up. I'm serious. Pause right now and do not come back until you know what isentropic means. You know what isentropic means? Okay. It means constant entropy, no change in entropy. How does that occur? That occurs if I've got adiabatic and it's reversible. If I know those two things, then I know it's isentropic. Now I'm drawing an arrow here, and we've talked about why it's an arrow. If you don't know why it's an arrow and not an equal sign, go look that up. There's a reason. Okay? We're saying that if you add up all the heat and it's not generating entropy, that tells you that the entropy does not change. Okay, so if it's ideal gas and it's isentropic, if these two scenarios are true, then that means if we write Gibbs Equation allows us to determine a change in entropy. If the change in entropy is 0, and we can also describe that change in entropy, I'm going to say approximately C sub P average ln T2 over T1 minus R ln P2 over P1. I'm going to derive this one first. Okay, so if this is true, then I'm going to move this minus R ln P2 over P1 over to the other side. I'm going to drop the approximately and I'm going to drop the average. But I want you to understand they're implied still there. Okay, so if I move that over, let's just write it this way. We'll say that C sub P ln T2 over T1 then becomes equal to R ln P2 over P1, right? And just move this over to the 0. And then I'm going to do a couple of things here. I'm going to say, well, and let's just move this over. Let's move the C sub P over. All right, so we've done some of this algebra before, some of this logarithmic algebra before, but I'll just go step by step here. So if I move the C sub P over here, so I've got R over C sub P ln P2 over P1. Now there's some cool logarithmic algebra stuff you can do here. We've got to brush the cobwebs off our logarithm algebra, and that's okay. If you're like me, it's not something you remember because you don't use it that often. But if I've got y times the natural log of x, that is the same as the natural log of x to the power y, and vice versa. This goes both ways. If I've got something outside of a natural log in an argument, I can bring this inside the argument if I raise the argument to the power of that value. And vice versa. I can take this exponent and move it outside of the logarithm, and that works either way. Also, if I take e to the natural log of x, that is simply x. Natural log and e are inverse, e to the power of our inverse functions. So one evaluated to the other just leaves the argument. Okay? So, some advanced algebra there. I don't know, mathematicians might say it's not advanced. For mere mortals, it's kind of advanced algebra, but it's for engineers, it's just what we do. That's okay. So, if I keep these two things in mind, so what I'm saying is if I take e to the natural log of t2 over t1, okay, then this is just t2 over t1. And so if I take e to this is equal to e to this, and I've not changed the equation, it's still the same thing. So, moving this inside the argument, e to the power of both of these, what does this mean? Well, this simplifies. So I just simply have t2 over t1 then is equal to p2 over p1 raised to the power of r over c sub p. Okay? Now, if that's true, and also another recall here, so we talked, excuse me, we talked briefly about the K ratio. I think we talked about this back in chapter 4 for us, right? The K ratio is the ratio of the specific heats for ideal gases, C sub P over C sub V. You can look up K. K is a function of the temperature, same as C sub P and C sub V. It's a function of temperature. It's actually simply C sub P over C sub V. Okay? And for an ideal gas, the difference between C sub P and C sub V is simply the gas constant, R. So if I employ these two, then I can say that this R over C sub P is simply C sub P minus C sub V over C sub P. And if I divide each of these terms by C sub V, right, so C sub P over C sub V is K, C sub V over C sub V is 1, C sub P over C sub V is K. So if I divide each one of these terms by C sub V, I get K minus 1 over K. Or simply that T2 minus T1 is equal to P2 over P1 raised to the power of K minus 1 over K. There's about 3 notes here, very, very important notes here. Right? Chapter 7 summary in 9th edition of Chengle and Bowles, at least the one I've got sitting in front of me, is wrong. I showed this to you in the last video, if you watched last time. Now, if you look in the chapter, where has he got it here? So if you look in the chapter, he's actually derived it correctly right here. This is what we've just derived. T2 over T1, P2 over P1, K to the minus 1 over K. That is correct. Now, if you go look in the Chapter 7 summary in the 9th edition, now, I've never noticed, I don't think this is, I think it's correct in the other editions. I remember I pulled it up and showed it to you guys on the video last time. I looked at it, I'm like, I don't remember what I said, but see, he's got P1 over P2 to the K minus 1 over K. This is incorrect. This is wrong. It should be P2 over P1 to the K minus 1 over K. It is correct in the chapter. It is incorrect right here. Okay? Now, these are correct. These should be V1 over V2. We'll look. Well, I'm not going to derive those, but I am going to leave this open because those appear to be correct. So there are other ratios here, right? So the Chapter 7 summary in the 9th edition is wrong, right? It's correct in the chapters. And I might have written it down on the last video. I might have, because I know I just went to the Chapter 7 summary because it's almost always correct. In the 9th edition that I've got in front of me, it is wrong. They may have corrected it a little bit, like there might be a 9th edition B that's correct. Anyway. This is only for ideal gas and isentropic. Now I'm stressing this important. Right? What you don't want to do is you don't want to go to Chegg or some online resource and ask a quote-unquote expert that may or may not have any idea what they're talking about, and they immediately go pull this equation and say, here's how you find P2 or T2 or whatever it is you're looking for. Because if it's not isentropic or it's not an ideal gas, this is garbage. Right? It's absolute garbage. Do not use this unless you know you can use this. And this is true, and the reason I'm stressing this is because you guys have access to all kinds of information that mankind has never had access to, literally at your fingertips. Only use anytime you encounter a simplified, really, really simple expression, you need to, as an engineer, alarm bells need to be going off in the back of your head of how in the world is this equation that simple? The reason it's this simple is because major assumptions have been made. This is only for ideal gas and isentropic. It assumes K average. Guess and check if you don't know both T's. Right? If you don't know both temperatures, you don't know K. So you're going to have to guess K to get a temperature and then use that new temperature to get a K. And we would have had to do that in the last problem. It would use, because it's assuming an average K value. Remember back here, I said I'm going to quit writing approximately and C sub P average. We're just going to say C sub P. Understand this was a C sub P average. So this is a C sub P average, this is a C sub V average, therefore this is a K average. Right? Now K will not vary as much as C sub P or C sub V, but it will vary with temperature. So if you don't know both temperatures, you will have to guess a K to calculate a T, and then use the new T to get a better K, and then repeat. It will go quickly, but you will need to guess and check if you don't know both temperatures. Okay, so keep that in mind. That's a common mistake people will make on the homework, is not guess and check the K value. Make sure you guess and check the K value if you want to use this, because you know it's ideal gas and isentropic. If it's not ideal gas and or it's not isentropic, don't use this. This is garbage. Again, when you see a simple equation, this guy's really easy to use, and he's got some friends, right? He's got some friends. If it's ideal gas and it's isentropic, T2 over T1 is equal to P2 over P1 to the K minus 1 over K. There's some other ones here. There's T2 over T1 is equal to this one inverse. This is little v1 over little v2 to the K minus 1. And then there is P2 over P1 is equal to, again, little v1 over little v2, and this is simply raised to the power of K. And through a similar derivation we just did to get this one, we could get the same, we could get this one, take this and this, plug them together, and you end up with this, okay? But again, these only work if you're dealing with an ideal gas and it's isentropic. And do not try to use these and plug these into the Gibbs equation of the second law directly. These basically become your second law equation if you're dealing with an ideal gas that's isentropic. Still use the first law, right? Use this in conjunction with the first law. Just understand this is the second law simplified for an ideal gas that is isentropic, going from state 1 to 2. And that's, again, that's a K average value. If you don't know both T's, you're still going to have to guess and check. Okay. So again, when you see a simplified equation, make sure you know the rules associated with that simplified equation. Same thing with like ideal gas law, right? Don't use ideal gas law on liquids or solids. Know the assumptions associated with the equation. All right, I got to stop you there. We'll pick up the next video.